it would be good for us to now go on to the normal distribution. Mathematica, what is the PDF of a normal distribution? What is a normal distribution? It's the classical bell-shaped curve. The parameters are labeled mu and sigma, in Mathematica at least. The mean and the standard deviation, not the variance, the standard deviation. The book labels them mu and sigma squared, the mean and the variance. But Mathematica uses this as the standard deviation as a parameter, though you do see sigma squared in this formula. That's a formula for the PDF of a normal distribution with parameters in Mathematica, mu and sigma, which do represent the mean and standard deviation of this, though that takes proof. It's suggestive notation for the parameters, but it does take proof involving integration, if it, at the very least, with them to come up with the moment generating function to confirm mu is the mean and sigma is the standard deviation. Actually, you can compute MGFs in Mathematica as well. That's the command. How about MGF? Yay! Oh no, it's moment generating function. I was wrong. Moment generating function, make it a function of t. That matches the theorem in the book. Let me call this m of t, define it as a function. There's this formula. That's the moment generating function for a normal distribution with mean mu and standard deviation sigma and variance sigma squared. Yes, we can confirm m prime of 0 is mu. M double prime of 0 is the second moment. If I take that second moment and subtract mu squared, I get the variance. Computational formula for the variance. And the square root of that is the standard deviation. It's very important to realize what the graph looks like. As mu and sigma vary, how about I put this inside a manipulate so I can watch what happens as mu and sigma vary. I need my x here, comma x. I got my square brackets messed up. Okay, I forgot the PDF. X going from, say, negative 10 to 10 or something. Well, let's try negative 5 to 5. Mu starting at 0, but I'll let mu vary to become negative, like negative 3 to positive 3. Sigma, the standard deviation, you don't want to be negative. This syntax is going to start it at 1 and let it go as low as, say, 0.1 and as high as 10. Don't worry about the syntax. I've typed this so often that I can do it pretty quickly. There's the standard normal distribution right there with a mean of 0 and a standard deviation of 1. And since the variance would be 1 squared, the variance is also 1. Bell-shaped curve. Centered on the mean. It's a symmetric curve. The mean is at the center of mass, which is in the middle, 0. The standard deviation turns out to equal the horizontal distance between the vertical line where the mean is and the inflection points on either side. Standard deviation is 1 here. What's the cursor? The horizontal distance between this vertical axis at the mean and the inflection point is 1. The inflection point for the standard normal curve is right about there. One inflection point, the other one's on the opposite side, right about there. The graph's concave down in between the inflection points. It's concave up to the right of this one and to the left of this one. If I change mu and sigma, it does affect the graph. If I increase the mean, the graph shifts to the right. It's always centered on whatever the mean is. I can make it negative. shifts it to the left. It's always centered on what the mean is. So the mean is a position parameter, you might say, the location of the peak. The sigma is a shape parameter. As you increase, it gets wider. Mathematica is changing the scale as I go because it wants to, but let me force it to stay fixed by putting plot range in here. If I increase sigma, the graph gets more spread out. The standard deviation and variance are both getting bigger. If I make it really small, it becomes a tall and skinny graph. Always, always the area under it equals 1, but that takes a lot of proof. You might wonder, it's kind of mysterious. Why is there a pi in this formula? I just watched a 3 blue, 1 brown video before class explaining this. I knew the reason from a multivariable calculus approach, but there's like deeper reasons why there's pi involved. I'm not going to get into it. If you prefer, you should watch 3 blue, 1 brown and look up normal distribution, and you'll see some videos about this. It's mysterious. Pi shows up everywhere in math. Remember some with the gamma function the other day as well, right? Gamma of 1/2 was square root of pi, I think. And we have a square root of 2 pi in here. It's so that it becomes a PDF, so the entire integral is 1. From minus infinity to infinity, there's area for all possible values of x, both positive and negative. You can do integrals in Mathematica to do your numerical approximations to probabilities if you want from this point on here, at least with this kind of problem. Or you can use the table in the back of the book, or you can use built-in functions in your calculator. Mathematica can also compute probabilities with probability. Syntax for that. Probability. Let's see. I think evidently you put the distribution over here. It's a little confusing. Look at an example. Okay, this is good. This is kind of nice. And if you're unsure how to get this funny thing in there, I'm just going to copy and paste it. So if I want the probability of x being less than or equal to 3 for a normal distribution with mean 0 and standard deviation 1, this should do it. Answer is going to be very close to 1, although I think it gives it an exact form, ERF. ERF stands for error function. Very close to 1 if we approximate. 9986. Graphically, you're at the tail end of the distribution. Almost the entire area to the left of 3 is going to be close to 1. And I can do that for any mean and any standard deviation. Say the mean is 10. Well, let's pick something else, 2. And the standard deviation is 1.5, which would mean the variance would be 1.5 squared. And actually, if I got a decimal in there, I don't need the / capital N. It'll do an approximation about 0.74. Can I do other kinds of probabilities, like being between, say, 1 and 3? Sure. There's the probability of x being between 1 and 3. Again, I don't know how to make that symbol offhand. I just copied and pasted. For the rest of class today, let's do some stuff by hand. In our textbook, again, the parameters in the textbook are the mean and the variance, not the mean and standard deviation. This varies by book. Some books do the mean and standard deviation, especially intro stats books. Because the standard deviation is easier to interpret. Remember the 2 standard deviation rule of thumb. It's easier to interpret the standard deviation as a measure of spread than it is the variance. So in the textbook, if x has a normal distribution, you denote that this way. You say x, well, tilde, capital N, with mean mu and variance sigma squared this way. That's the mean. And that's the variance. And so, yes, that means the standard deviation is the square root of whatever's there. I showed you how to use Mathematica to compute a probability. Let's do a probability with the calculator as another example. Say X is normal with mean, what was the example I just did? Mean 2. And variance 1.5. Should we do that? Sure, why not? Well, let's make it come out nice. Let's do variance 1.44. So that means the standard deviations. This is sigma squared. So sigma is the square root of 1.44, and that will be exactly 1.2. I'm trying to make it come out nice. And what's the probability that, say, X is between 1 and 3? Well, maybe negative 1 and 3, just to make it a little different. Make it not centered on 2. Quickest way to get the answer with your calculator. Go to your distribution menu, CDF. It by default leaves the lower limit as essentially negative infinity. Negative 1e99 is the calculator's way of representing negative infinity. If I put the number 3 here, for example, that's computing a CDF value, capital F of 3, with the given mean 2 and standard deviation 1.2. The calculator wants a standard deviation, not a variance. So this is capital F of 3. It's not the final answer. But, I mean, I could also compute capital F of negative 1 and then do a subtraction. Might as well. Oops. Did I do that right? Did I do a 1 or a negative 1? I did a 1. Okay. Okay, very small. It's approximately 0.7977 minus 0.0062. Can I do that in my head? 0.7915, I think. But you also could just do normal CDF as it is. Change the lower limit of integration to negative 1 and upper to 3. This is computing the area under the curve between those two values. Hopefully close to 0.7915. Yes. I would recommend also using the normal table in the back of the book, though if you do so, how can there be just one table? You got to standardize, convert to Z. And even though we have our technology, this is something you should be able to do. Remember this formula? Z equals X minus mu over sigma. You can use this formula for any random variable. You can always subtract its mean and divide by standard deviation, assuming those numbers exist, and effectively standardize the value. However, this is almost always done just with normal distributions. And so almost always Z represents a normal random variable. In fact, with mean 0 and standard deviation and also variance 1. I'm going to write the 1 as 1 squared to emphasize that our book thinks of it as a variance, but of course 1 squared is 1. So this probability can be standardized by applying this formula. With both of these numbers, negative 1 and 3, use this formula. Subtract the mean of 2, divide by the standard deviation of 1.2, and do the same for the X, and it magically morphs into a Z. Why does it magically morph into a Z? Because we say so. Because that's what Z is. It's X minus mu over sigma. As long as I do it to each term in the string of inequalities here, it's still, these are still equal to each other. That's negative 3 divided by 1.2, negative 3 divided by 1.2, negative 0.25, negative 2.5, I mean. Here, 3 minus 2 is 1 divided by 1.2. That would be 5/6. That would be 0.83. Repeating. So if we used our calculator with the normal CDF, change the lower limit to negative 2.5 and the upper limit to 0.833333, change the mean to 0, change the standard deviation to 1, we should get the same answer of 0.7915. Yes, we do. And you can also use the table in the back of the book to confirm this. Effectively, the table in the back of the book would give you these values again, and you have to do a subtraction. This is really capital F of 3 minus capital F of -1, where capital F is the CDF. It's worth mentioning that the CDF of a normal distribution has a special symbol. I will mention this next week as well. Capital Phi. Oh, Greek letters. Actually, capital Phi always reminds me of the Mario Donkey Kong squishy thing. You know about Mario. Also Donkey Kong from a long time ago. Okay, that's the special symbol for a standard normal CDF. Standard normal CDF. Very quickly, in 4 minutes, I'm going to mention some other things you should be able to do for the assignment due next Tuesday. And these are easier, technically. Well, at least the first thing is easier. You should be able to use what's called the 68, 95, 99.7 rule. By the way, when you do this kind of thing with a normal random variable, the result is a normal random variable. That is a theorem, standardization theorem. It is something we haven't proved yet. We'll prove it in chapter 7. Proof of this very important fact is in chapter 7. When you standardize a normal random variable, you also get a normal random variable. There's the 68, 95, 99.7 rule of thumb. It says if X is normally distributed with parameters mu and sigma, the book is inconsistent there. They should use sigma squared. Mu and sigma squared, the probability of being within one standard deviation of the mean is about 0.68. To be within 2 standard deviations of the mean is about 0.695. That's analogous to our 2 standard deviation rule of thumb that we mentioned. To be within 3 standard deviations of the mean is about 0.997. Our textbook is written, I think, by engineers. As this is stated, it's not really a theorem, because theorems don't involve approximately equal to signs written with dots above the equal signs. It's not really a theorem in the traditional sense of the word here. It's a result, as Dr. Wetzel would say. It's good enough for practice. So if you got a situation where you're wondering what's the probability of being within 2 standard deviations of the mean, where you know the mean and you know the standard deviation, it's about 95%. Of course, you can also use your calculator or the table to compute it. Actually, this one's a little bit bigger than 95%. It's almost halfway to 96%, but it's still closer to 95%. Should be able to do that. That's the easiest one. There's something called Chebyshev's inequality, which is not that hard to be able to use. You just have to know what the K is here. This is the probability of being within K standard deviations of the mean for any random variable with a finite mean and a finite standard deviation. Notice there's nothing about normality here. Just plug in the value K. So this would give you a lower bound on the probability of being, for example, within 1.5 standard deviations of the mean if you took K to be 1.5. Just plug it in there. Final thing I want you to be able to get basic problems about, and this is very historically important. Not so important these days because of technology, but historically, this was part of the motivation for the normal distribution. Gauss, I believe, discovered this fact. that if X is a binomial random variable, discrete, chapter 3, counting successes in n trials, with parameters n and p, and well, for large n, the conclusion is X is approximately normal with mean n times p and variance n times p times 1 minus p. Wait a minute. The first thing that should pop in your mind is, if X is binomial, how can it be approximately normal? Because binomial is discrete and normal is continuous. Well, if you graphed bar charts, histograms for your binomial random variable, which we've never done before, but we certainly could have, both the heights and the areas of each rectangle represent probabilities. So for example, this one, the height of this, no, it's not the height. Okay, no, it is the height, because the base is 1. The height of that one is close to 0.25. So for this example, the probability that the binomial random variable equals 4 is close to 0.25. N is 10 and P is 0.4. If you make it as a bar chart here, it looks like kind of like a normal curve. And the bigger N is, the more it looks like a normal curve. And areas under the normal curve, therefore, can approximate areas under this, and therefore probabilities. But it's tricky because you have to use something called the half unit correction for continuity.